Madam, please start.
Okay, thank you. Myself, Anagha Malkapurkar, Assistant Professor from EXTC Department, AC Patil College of Engineering. Warm welcome you all. Respected faculty members, organizing committee members, distinguished guests, and dear participants, good evening. On behalf of the organizing committee, it gives me great pleasure to warmly welcome all the respected faculty members and distinguished guests, Dr. Sushil Kumar sir. Sir, your presence and guidance mean a lot to us, and we are grateful for your continued support and encouragement. Today, we are truly honored to have with us an eminent scientist and researcher, Dr. Sushil Kumar sir from CSIR National Physical Laboratory, New Delhi, as our esteemed speaker. Dr. Sushil Kumar sir is currently serving as a chief scientist at CSIR NPL, and he is also an honorary professor at the Academy of Scientific and Innovative Research. At present, he is heading the Advanced Material and Device Metrology Division at CSIR-NPL. Dr. Sushil Kumar sir obtained his PhD in Electronics Engineering from IIT Banaras Hindu University and joined CSIR-NPL in the year 2000 as a scientist. He has also gained valuable international research experience through his work at CNRS Laboratory, Paris, France. With an impressive academic and research profile, he has over 200 publications in reputed national and international journals and conference proceedings, along with 10 patents to his credit. He has also contributed to the scientific community as an editorial board member of several journals, including the Journal of Nanomaterial, Vacuum, and the Indian Journal of Pure and Applied Physics. Currently, he is a steering committee member of PTB Germany for a solar PV project and is actively involved in the International Clean Innovation Research Network project supported by the Australian government. He is also a technical committee member of International Measurement Confederation Germany under TC20 measurements of energy and related quantities and serve as an expert member on various national committees related to solar photovoltaic technologies. His current research interests focus on emerging heterojunction photovoltaic devices and the recycling of end-of-life solar panels, contributing towards a sustainable circular economy. We are indeed privileged to learn from Dr. Sushil Kumar Sir's vast experience and expertise today. Sir, I warmly welcome you. Sir, as per the schedule, the session is planned for 1.5 hours, concluding at 9:30 p.m. And we would be grateful if the final last 10 minutes could be reserved for an interaction and question answer session with the participants. Once again, I extend a warm welcome to our respected faculty members and our today's eminent speaker, Dr. Sushil Kumar sir. Sir, thank you. And now I invite Dr. Sushil Kumar sir to begin his talk. And also, it's a wonderful learning experience for all the participants. Thank you, sir. Sushil Kumar, sir, can I hand over to you?
Yeah, sure.
Yeah, welcome, sir. Good evening.
Yeah, good evening. Thank you for introduction, and I would like to thank organizing committee for inviting me here to
Welcome, sir.
present my talk. Just a minute, I am loading my talk.
Yeah, no issue.
Mm, Yes, please confirm. My slide is visible.
Yes, sir, it's
Yes.
visible.
Okay, thank you. So I'll begin my talk. Uh, as such, the topic I have suggested solar cell design and fabrication. But I'm going to cover you these things as well. Particularly, I will emphasize about the advancement in the technology and what are the challenges there in solar cell. And you know that the solar cell is not now the emerging technology; it's already mature technology. I can say you, particularly to one of the kind that is the crystalline silicon solar cell technology, and still lot of R&D is going on. And because of that, some new designs and researchers are hunting for not only for improvement in the efficiency, also the reduction in the cost. And that is what you are seeing nowadays in the recent past, that one of the issue that we are facing, the climate change. And for that mitigation, the one way is to use solar panels for generating energy, and that we say is a green energy, but of course it is not that green. It has some issues that will also I cover in this my talk. So this is how I have planned the solar photovoltaic to mitigate climate change and the shortage of energy basically. And then I will talk about solar PV, some basics, because I thought that this is a faculty development program. So that is why I will go with some basics. And then I move to the choice of materials and the technology for solar cell, what is available now, and what are the parameters on which is depends what kind of a material it's work for solar cell and how we can move on. And then I will discuss about solar cell design and fabrication aspects of crystalline silicon, thin film, and some of the emerging PV. Particularly the crystalline silicon and the thin film, they are the mature technology, commercialized technology. Of course, the market share is more than 97% now of crystalline silicon. And then finally, at the end, I will also cover some of EOL, that is the end of life of PV panels, because I believe this is also important to understand the things. And here also a new design is needed, so that whenever we are going for facing of a end of life panels, that is the waste panels, so that we can easily recover the material, that we say the reclamation of material and easy recyclability. So that design is also needed. And finally, I will make my conclusion with some summary. So this is what I'm going to move. And I always prefer to show you just to motivate us. As we know that whatever we are here, we are already motivated. But still, I like to begin my presentation with this slide. If you see 1928 and the now, the same location, the picture taken about a century old, you can see there, and it's the difference. So this basically gives us a things what happening here on our earth, and that motivate us to think how we can mitigate this. Basically, it's not, the second picture looks good, nice, of course, to me also, but somehow behind the thing it is not good. And the issue is basically we want to use lot of energy for our comfort life. This is what we have invented, discovered many things, and energy is needed. But along with that, we have also generated the problem because of the lot of generation of CO2, and we need some mitigation for that. We all are very concerned. So this is how I feel the shortage of energy and the climate change. These are the things, because we are using a lot of fossil fuel, and which is, of course, it is a limited. And you know that the recently even a lot of means things happening even just 2 days ago also happened because of fossil fuel. Still it is known that it is limited. So our aim is to reduce the CO2 emission drastically, because we want to keep our Earth's temperature 1.5 degrees Celsius. It should not exceed now. So that is what is emergency scene. And now we are in the era of energy transition from fossil fuel waste to green energy. And one of the way we adopted the solar panel, there is a paradigm shift now, energy transition. This is how it is now. This is what happening even in India also. more than 50% now, exactly 51 point some percent is there of renewable energy. So we are also shifting towards green energy. But of course, as I mentioned, the end of life is the issue also there. But yes, right now it is a good thing to move towards all the renewable energy, and the PV panel, solar PV panel is the one way of generating solar energy. And this data I like to prefer to give you for the urge on global RE or the PV power capacity. Basically, if you see that global renewable power capacity of 4,448 gigawatt by 2024, and out of that, solar power is the maximum. If you see, and it is already basically now it is crossed 2 gigawatt at 2000 terawatt already crossed. This is little old data. Still, the full scale data is not available for 2025, and the target for 2030 is 11,000 gigawatt. So major factor which is supporting for green energy is the solar power. This is what we are seeing. And alone in 2024, the maximum power capacity is also added of this solar PV. And we in India also, if you see, the more or less the same scene is also here. And now we have a 262 gigawatt by 38 November 2025, this year on, and we are targeting for 500 gigawatt. And if you see that in terms of percentage, here also the solar power is maximum. The 132 gigawatt is already added here for the solar, and we are targeting for 300 gigawatt. So this is basically a sign where we are seeing that solar power is the maximum push globally as well as in India there. We are moving for our energy requirement. So, and even if you see the world photovoltaic installation capacity, we are at the third position. This is now it is 132, and after the China and the US, this is for European Union data, and this is how cumulative it is added. Now it is 2.2 terawatt for 2024 data, and estimated it will be around 9,500 gigawatt by 2050. So all these good thing happening, and also projection is that we will have more and more solar panel installation. Now, this is normally we understand the solar technology. We have a one side photovoltaic technology, otherwise solar thermal technology. But I'm going to talk about this solar photovoltaic technology. Essentially, it's a semiconductor material we take, and the photo generated carriers are created. We create electron and holes. This happens after light absorption in the semiconductor material, and then we separate these carriers to a conducting contact. This is how the solar cells works. And when the solar cells are fixed in the module, they are connected in series or the parallel, depending upon what kind of a power requirement we want in terms of current and the voltage. We have the module, and then we have the array, and then we have the system. Basically, it's all things known. Here, the important thing, in the solar cell, basically we talk about the efficiency parameter, only the efficiency parameter, but in the module, we talk about the power. Now we have a more than 500 gigawatt, even 700 plus gigawatts are available. And the performance parameter for any, either the solar cell or the module, is very, very important. And ultimately, it's depend upon what kind of a material we are using, and how our design structures of solar cell are there, how pure materials we are using, is decides the parameter of any solar cell. Now, in the solar cell, yeah, this is for the crystalline silicon. You know that well-known structure for this is your cell. I will talk about the individual layers of cell later. Here I am talking about first the module. Basically, these crystalline silicons are the discrete connected modules. Since my topic is the design and fabrication, that is why I want to discuss this. Here, you have a cell, and this is crystalline silicon solar cell, and they are connected basically one after there, whether you can have a series or the parallel connection, the way we can make it. But in the one line, you have a series connection here. Basically, these are the copper lines, copper grids, which are connected there. And these are called discrete connections. Basically, the cell is there, one cell after cell, it is connected from the outside. That is why it is called the discrete connections here. And when they are connected, after that you need to encapsulate it with the EVA polymer layer from the top and the bottom side. Then you have a tempered glass, the frame adhesive aluminum frame. This is how all they are. So most of the innovation in recent past, what that happened particularly in the cell design, though there are large number of components in the module which we are using it, that is what it is being used for electricity generation. But in last 10 years, or if you see earlier, we had a BSF back surface field, then the PERC, now the TOPCon, HIT solar cell. Then many solar cell designs are there. I will discuss one after other. But maximum innovations that has taken place in the solar cell, not much in the module. But of course, the in the module also we need some good designs and easy to break it at. I will talk this thing in the later stage of my talk because that's the important component even there. But unfortunately, globally, there not much research is going on. We are following more or less the conventionally same thing. Of course, some improvement has taken place in the glass, that too for the anti-reflection coatings or some added material there like antimony, so that we can have a more transmission as an anti-reflection, and some in the ethyl vinyl acetate, that is the polymer. Good polymers needed. Some innovations taken place in the recent part, adding some other polymers there. And in the cells, of course, lot of things happen. I'll talk that. And now I'm coming to another thing, that is basically I talked about the discrete connections, but here I'm talking about the monolithic integration. That is basically that takes place in the thin film solar cell technology. So here the cells are not separated. Basically, when you are making a cell, at that time, layer by layer you are growing and they are interconnected. Because suppose this is given for the amorphous silicon technology. It's a quite mature technology, and once upon a time, just 15 years ago, this was much ahead in thin film technology. But right now this technology is not in the market. But of course, the amorphous silicon as a photovoltaic material is there in the crystalline silicon, like in the HIT solar cell, and also in the tandem junction solar cell. It is being used with the silicon cell technology. So as for the photovoltaic material, amorphous silicon is there. So here, if you see this structure, basically you have a glass there, you have a TCO coating, and you need to scribe the lines there so that you can have a separate source. And then you have a semiconductor material. And normally these are in the PIN structure for amorphous silicon, but for other material like CIGS, you have a PN structure that is grown, and again you need to scribe, that's pattern 1, pattern 2, and after metallization you have the pattern 3. So basically they are interconnected. If you see, this is connected in the series. Whatever electron and hole pair created at the junction, they will travel here one after other cells, and they are separated there. So this is how collections of carriers are made, and these are called the monolithic integration. So there we have a discrete integration. Here we have a monolithic integration, and the monolithic integration is used in thin film solar cell. So this is how it is different. These are the two different technology, and different design is needed for making of a solar cell. Now, the choice of solar cell material, basically that decide the kind of solar cell technology. And we all know that in the silicon we have a monocrystalline, multicrystalline, but nowadays multicrystalline is almost gone from the market. Only monocrystalline silicon is there. Earlier we had amorphous silicon and the microcrystalline silicon, and even the CIGS, CIGS, CDT is there. The one company is there, that is First Solar in US. Also, we have the plant here in Chennai, CDT modules. They are the thin film technology, and high efficiency gallium arsenide. Basically, these are for the space application. Compound semiconductor based is quite popular, and it's being used for the space application. So these are called the second generation. Other one is called the first generation technology, and 97% of the market share is of first cell and the thin film. Another, these are dye-synthesized organic perovskite quantum. They are in the lab and at the certain level in the pilot scale. They are not mature technology, not commercialized. Yes, these are the third generation solar cell. There are some standard for measuring these under the STC standard test condition for these. The standard for crystalline silicon, standard for thin film solar cells are available, but for emerging there is no standard. But some protocols are there. They are defined in the literature, and everyone follows those things. So this is how it looks like. The different you have a solar cell material and the technology. Just I discuss about the first generation, the second generation thin film. Here we have a gallium arsenide, amorphous silicon, cadmium, and copper India. In the amorphous silicon, microcrystalline silicon or nano or some nano. Here in the third generation, these all emerging, though dye synthesize is there since long, about 30 years now, but still not commercialized. Organic photovoltaic, perovskite, and multi-junctions are there. Multi-junctions, basically, I'm talking about the tandem and other things here. So these are the basically the choice of material. So it's depend which kind of a material we are going to use for making of a solar cell and how the technology will evolve from this. So this is also I always prefer to show the NREL efficiency chart, like the record efficiency, like we have a records for our different athletics games or the cricket. The same way NREL produce even for different technologies, how the efficiencies improvement with time it has taken place. Now, the type of cell structure. Basically, now we know that we are going to use the material. How we can have the solar cell. For definitely, it should be absorbing material, semiconducting material. We can have a homojunction like the crystalline silicon solar cell. We have a P type or the N type. In the amorphous silicon, we have a P type and the N type, and in between we have intrinsic layer. So here basically it is a diffusion assisted conduction takes place. That is why it is preferred to have a PN junction. Here it is a drift assisted because these are very defective materials. It's not that good material. Normally it's a non-crystalline material. So that is why we need a drift assisted conduction. So we introduce a thicker layer of intrinsic layer and then P and N layer. Even in the perovskite solar cell, we use such kind. Even in organic solar cells, such structures are used, even in the PN junction form. In the heterojunction, like in the CDT and CHGS, these are polycrystalline material. So you have a P type and the N type. In the multi-junction, you have a different layers with cells. Like in the multi-junction, you have a one layer, one cell, two cell, three cell. These are also multi-junction solar cell or the tandem solar cell. Here it is shown for three cells. So your top cell should have a higher band gap compared to second cell, and second should have the higher band gap compared to third cell. So this is how normally in the design we choose, because the energy higher band gap, basically the higher energy get absorbed in the first cell and then to the second cell and the third cell, so that maximum energy you can absorb here and you can have a more efficiency. So typically multi-junction solar cell gives more energy compared to the single junction solar cell. Like here it is given for triple junction solar cell of the gallium based. You see the gallium indium phosphide, gallium arsenide, and the germanium. They cover these spectra, blue, green, and the red. Yeah, it is shown. So this energy can be used in the solar cell, like here it is shown, having the different band gaps. So this basically the combination, the combined effect gives you the more efficiency in the solar cells. So this is the important design aspect. I'm not going to present here for the simulated result, though I have published a lot of paper also in the simulation, but I thought to emphasize more on the fabrication part and other thing. So I'm giving you the glimpse here, what kind of a solar cells we have. So like in the organic solar cell, either you can have a donor receptor in the active layer itself. There is, it's not defined, means well-defined layer here. It's the N-type layer and the P-type layer. Basically, they are embedded there, and excitons produced there, and they get separated here itself, and they collected at the cathode and anode. Here you have, like here, the acceptor or the donor. So this is how the different structures can be used. You can have a PN there in the material itself. In the dye synthesized solar cell, here is like used there, the TIU electrode in the electrolyte it is being used. And even in the perovskite, if you see here, it's basically is a PIN kind of a structure. You have a ETL and STL on the one side on in the absorber like a perovskite, and perovskite methyl ammonium lead iodide is basically now we say it is a conventional perovskite material because that gives more efficiency. Whatever the efficiency you are hearing is because of the methyl ammonium lead iodide, but other issues are there, stability and scalability are there. So this is how these cells are made. Now I would like to give you some comparison between the lab and the module, lab cells and the best lab modules. So always there is a difference between cell and the module. Like here it is for shown for the monocrystalline silicon. The two defined area, 134 centimeter square and this much is much larger. The efficiency is reduced. You can understand there is a loss always in if you have a larger area there. Even in the for the CIGS for small cell and the big cell, it's basically the module, and then CDT cell and the module. The module efficiency is always low compared to the cell efficiency. Even for the perovskite, it is shown here 26.9, 19.2. So quite much difference here. So because there's a lot of research has taken place, technology is matured, so not much difference nowadays. It is observed in with the cell and the module, but here in the perovskite it is quite obvious. A lot of R&D is going on. Module integration, monolithic integration. Here you have to do it is all there. Even in the tandem solar cell, some difference is there. So basically, this is the perovskite and silicon. These technologies are not mature technology. Basically, these are not commercialized, I mean to say. It's all laboratory based or some certain level pallet scale. So it's still a lot of research need to be done in the perovskite and silicon tandem. But this is the thrust area. Now more people working on the perovskite and perovskite with the tandem. This is how the industry is looking because the silicon technology already a lot of manufacturing capacity is there, and the same capacity can be coupled with the perovskite, and industry is looking forward for so that if this technology comes in future, may possibilities there. But unless the perovskite stability and scalability, two issues are there. Stability is the major issue. Unless that is solved, it is not going to come in the market. This is what even for the 3.5, if you can see the 1 centimeter square and the larger area, some efficiency difference is there. So this is latest data from Fraunhofer, is in German laboratory. And this also I like to show you. Basically, it is the how things have improved. So a lot of research went into the passivation at the back contact. I'll just demonstrate you with one slide there. Uh, Basically, you know that in the back surface field, the back side, most of the recombination losses that happen in the solar cell, when light get absorbed, you have electron hole pairs creation there, but it is not that all the electron and holes will be collected at the contact layer. There may be some losses that is called the recombination losses, and the maximum loss occurs at the rear side. And if the proper passivation and other things are there, then you can have the improvement in the efficiency. And this is how it is happened with time. Whatever the technology you are seeing after the BSF, back surface field, the PERC, or even the TopCon and different version of the PERC, like Pearl and the PERT, even in the heat solar cell also, basically the passivation that work a lot for the improvement in the efficiency, close to 27%. So it's all because of the R&D happen in the lab. Now, this is just to make you more understand. Basically, we have a PN or the PIN junction. So this is three things is important: the absorption of photons, separation of electron hole pair, and the collection of charge at the electrode. So just now what I was discussing, the different solar cell technologies strive to maximize the efficiency above three operation in a different way. That's what our always aim to design a cell. Like here it is shown for a conventional solar cell, you have a P and N type. material. Basically, in the silicon technology, you have either a P type or N type. Then we do the diffusion from the one side, and we make a junction there, and then we go for other things like maximum absorption, because we put some anti-reflection coating, silicon nitride, and then we have a contact. Before that, we also do some passivation of materials, so that we can have a more absorption there. Means basically light should not get reflected back. And then we have a proper contact, so that we can, and a built-in potential there, proper junction, so that you can have a proper separation of electron hole pair. And if you have a proper ohmic contact with looking proper work function with the semiconductor and the metal, you can have a good collection of the charges. This is how for we go for any design of the solar cell. These are some IV characteristic solar cell and the performance parameter. I think all participant must be knowing it, but even though for some who want to refresh himself, whenever you have a solar cell, essentially you need to see the IV characteristic of that, and that decides the performance of it. And this is how it looks like. You have a IV characteristic. These are the some important point: ISC, the short circuit current. You have a VOC, and if you know the area of the solar cell, then you can, and your incident light intensity. So this way you can measure the efficiency of any solar cell, and basically this is your load point, P maximum. That's the interesting point for any cell, and this decides the how much power you can draw from this uh, cell. And so this is how basically the light, your input there, and the output. So ultimately, it is the current, basically, what it is producing in the cells, that is the most important. And the well-defined optical input, the input that one has to be sure about what energy you are using it. And the current meter and the voltage source by which you are measuring it, the current and the voltage, because the VOC, IOC or ISC maximum, VOC maximum, all IV characteristic is plotted because of you have a current meter and the voltage source. And then area of the solar cell and the test, that is also very important to accurately measure, and the temperature sensor, because the measurement has to be done at 25 degrees Celsius. So that's basically the efficiency parameters. So this way we measure. In NPL, we have some facility. Just quickly I will go, the solar simulator that we measure with the standard test condition. Now, another important point, we all know that for the measurement of solar cell, you can have different intensity level, 1 sun, 2 sun, or the half sun or 0.25 sun. Ultimately, basically, it is the energy. Like if the standard is 1 sun, that is 1000 watt per meter square, or 100 milliwatt per centimeter square, that one should use. And also the maximum matching of solar spectrum. Like here it is shown for the AM 1.5. So this basically, if you have this well calibrated your lamp and you are doing the accurately measurement, then only you can say is sure about your parameters, what you are getting from your cell. The AM10, AM1 or AM1.5, but AM1.5 is the standard that is being used. Basically, AM1 is 1 by cos theta, where theta is the angle of sun rays with respect to your G net. This is how it is there. So this is how the standard wavelength is being used. And basically this is for NPL, what we have our expertise, different parameters with different range. So, and we have also developed primary reference solar cell calibration facility at CSR NPL. Actually, today only this was inaugurated by our Honorable Minister Jitendra Singh Ji. So that is why I thought to show you this is an important national facility, and it's fifth in the world. And but our efficiency, this uncertainty parameter is best among world. We have compared with TIPS China, AST Japan, NREL, and PTV Germany. We made inter comparison with NREL US and the PTV Germany, and our uncertainty in the measurement found to be the lowest among world. So we are the fifth in NPL. It's a national pride. So solar cell calibration can be done for reference solar cells. Now I'll go some more some basic. You know that the solar spectrum you have chosen your A1.5, all those things are there, and you have a material. Now, what's the band gap of your material? Like if I show you this curve first, this is how where this falls on your solar spectrum. This is your solar spectrum, right? And different band gaps. So ultimately, basically, the structure of the material that decide the band gap, and that band gap will decide how much your solar spectrum is going to absorb, and that is only the useful thing it is going to happen for the solar cell. So it means the photon energy is lower than your band gap, it is not going to be useful. Basically it will weakly interact and it will pass through your solar cell. If it is equal to, then it is enough energy that will create electron hole pair. Basically this is important. Even if it is greater than your band gap, it is not going to be useful. It will basically generate the phonons, and it will basically thermalization will occur, and this will be a waste. So basically this much energy will comparable to band gap. So that's what it is important. Whatever material you are choosing, first you have to see the band gap of that material, then only you can go for design of whether it is a PN junction or PIN junction in any form. And what is your absorbing material? Basically in the solar cell design, essentially we have some material we call as the active material, that is our absorbing material, where our solar spectrum get absorbed. And then you have a junction there, huh? And junction basically develop a depletion layer that is produce a built-in potential, and that separate your electron hole pair. And the separation, during separation and its movement along your layer material, there has to be defect free and no recombination losses. That's the ideal condition basically we want. And then its collection. So this way one can design any solar cells. This is what basically the lattice thermalization, junction voltage drop, contact voltage drop, or recombination, non-absorbed photon. So basically, this is standard for any. This is basically these are the losses that happens in solar cells. And what best efficiency is possible, it's also decided by the its material structure. And, and of course, some improvement if you are doing by adding some layer, like I mentioned, the passivation or the anti-reflection coating and proper contacts, you can have some good collection, and then you can have a good efficiency. Means the more collection means more efficiency. This is how. And ultimately you need some resistance there also. It is not that only the semiconductor will work there. So this is how the quite old Shockley and Quasar. Maybe those who are in the photovoltaic must be familiar with this thing. The efficiency for any single material, it was predicted at 33%, AM1 at AM1.5. For silicon, it is 29.4. Best silicon efficiency, now it's already achieved 26.7, even 27 point plus for HIT solar cell is there. But since in the HIT silicon plus amorphous silicon are there, that means the 90% of theoretical efficiency is already achieved. Okay, so all very little scope is there. So that is why more emphasis is happening towards some other materials or some compound semiconductor or some tandem junction solar cell, more than one cell. This is how the thrust area nowadays is there for making of a solar cell. The silicon, just quickly I will give you, you know that the silicon is very important. Silicon technology is there. It is not only in the solar, even the electronic also used. It is extracted from silicon, metallurgical grade silicon is, then purification and all those things are there. And you have a silicon it get using, basically before that you have a cement process or a rusty process. So basically the silica we get is a in pure silicon, and from we react with carbon so that you have a CO2 produced, and then silicon is there, metallurgical grade silicon comes. And then we go for the cement process. There we produce about 4 to 5N purity silicon. It's a polycrystalline silicon. Then finally you have to go for Swarovski process or the flotation process to formation of the ingot. And you have an ingot, then you make wafer, and finally the cells and the module. Now, So for the conventional solar cell design, I will go now one by one, some silicon solar cell technology, basically the cell, how it is designed. This figure is shown for it's a conventional, basically the BSF solar cell. It was there for many years, but recently now it is out of the market. Other technology with little modification in the cell, but primarily more or less these are the still there, but in the back contact, in the some front side, some modifications are done. Basically you have a silicon there, either you have a p type or n type, like, and then you go for texturing of it, uh, because texturing we want so that you can have a multiple reflection over the surface, and so that you can have a more absorption there. And also it basically gives you some anti-reflection properties. Nano texturing is also possible to do. And then you go for the like here it is p type, and then you go for phosphorus diffusion. Here it is shown for POCl3 that is being taken, and you basically this process is done at 900 degrees Celsius, and there you have a n layer of silicon form, and then you can remove the parasitic junctions there, and then over that you can make a silicon nitride coating. Basically it's a amorphous silicon nitride coating by the PCVD process, that is plasma enhanced chemical vapor deposition. This blue line over it is shown here. This is your anti-reflection coating. And then you can have a metallization, that is normally it is the silver it is being used, and at the back contact you have aluminum. These are the called fingers basically, because we don't want to opaque all the layer. Some transparent, basically some open space is needed. So essentially basically more finer the line, you have more light can go inside. But basically it's a trade-off. You have to optimize what could be the thickness of your lines. Otherwise light will this material will make opaque for light to go in, because metal is reflecting there. So it is basically from the open space, light go inside and it gets absorbed, and you have electron hole pairs and then separation. So this is how it is there. So you have a fingers, and then all fingers are connected with one again metallic line that is called the bus bar. So it's a conventional design for silicon solar cell. It's a textbook design. Okay, in NPL also we have worked for industrial silicon photovoltaic for 6-inch by 6-inch. There we did nano texturing. Basically, these are nano wires based. Just I wanted to show you this is also one technology. But somehow this is not commercialized globally. But yes, texturing is there, but not that finer technology, because this has some drawback. Because this gives you better anti-reflection coating, but this also makes reflection, basically the recombination side. The more when carrier comes there at the contact point, some losses are there. So basically, it's a trade-off. No, so more absorption is there, but because of the nano texturing, the surface area, some basically you know that the unbroken bonds are there, so rough surface are there, dangling bonds are there. So they are the recombination side basically here, and that is why some losses are there. So some still R&Ds are going on so that some improvement can take place, but reflection losses is quite low here there. Okay, so this is basically now I'll give you some more details about analysis of recombination losses. If you see this pie chart, basically it's a very important chart where this basically we are losing our carriers. In the back contact, about 49% we are losing. In the front surface, only 11%, in N plus region, 13%, and in the absorber P region, 26%. So maximum losses is occurring at the 49% here. You can see that. So this is how the most of the work in recent past, though the technology was invented long back in 90s by Martin Green from Australian National University, that PERC solar cell, but in recently about 7-8 years back that come into the industry. So they work that basically more in the design, how we can minimize the back contact loss. That was the technology. Here, if you can see, it's not there. complete layer of your contact material. Basically, the grooving is formed, the diffuse hole contacts basically. So if you see the silicon wafer is there, diffuse electron contact is, that is the emitter layer that I've shown you, the POCl3 base, basically the passivation and the anti-reflection metal finger. But here it is a difference. If you see the diffuse hole contact and the passivation also it is there, and then the back contact. So basically it is what it is happening, this increase the surface recombination velocity and collection is more, and recombination losses is less here. So this is happened because of the dielectric layer surface passivation. So basically you have some surface passivation. This passivation maybe one can use AOL2O3 or some other dielectric material is also, sometimes SiO2 is also some industries are using. So this is for the passivation. The back surface passivation is very, very important. And then you have a close contacts there, so that you have a carrier collection is also there, and you can minimize the recombination at the rear surface. This is what this technology basically evolves. Three things, three technology that is more or less quite close there. The PERC, you people might have heard about that, PERC, passivated emitter rear contact, or the PERC passivated emitter rear locally doped, or the PERC passivated emitter rear totally diffuse. And the restricting the aluminum alloy P plus region, that was at the rear side to a small fraction, about 1 to 5%. This is what I am showing here, 1 to 5%. It's not completely basically. And of the rear surface while passivating the rest within. And in the basically these are the laser ablation. These grooves are formed with the laser. Like for the typically 6-inch cells, it is shown, but nowadays M10 is also being used. Like 1130 local contacts openings were there, it is made in the insulator. So this is how basically these things in the rear contact, these innovations have improved the efficiency of solar cell. What it was in 2014, 2015, about 17-18% industrial solar cell, and is gradually now moved to 23-24%. 22-23 is easily now commercial models, big size models are available. So this happened because of this innovation in the rear contact. Other thing, this is basically how it is shown here. For the pearl, you have a local diffusion here, then you have a contact here, rear contact, and these are the oxide basically is grown here. In the PERC, this is how the grooves are formed, and even in the PERT, you have a P plus here. So this is how it is, basically some little bit differences, but the PERC is very common now. It's about 70% now market is of the PERC solar cell. And now just 1 or 2 years back, and now TopCon is coming there with little difference. Again, I say, like here I can show you, it's a difference in the, you have a basically thin layer of SiO2. This is what it is given in the TopCon solar cell. So this how the difference. So now more market share is coming for the TopCon solar cell. So these are the innovations. So what I am emphasizing here, and this is compared with the PERT solar cell. Even when the bifacial solar cell, you know that you can get absorb your light from both sides, front and the back side also, and it can improve your efficiency. Basically, you have to make the contact and the other N plus layer there. So P plus layer, N plus layer, if you see, and this is the silicon main absorbing layer. You have anti-reflection coating there at the top, also at the bottom, and then at the contact. So this is how the comparison between monofacial and the bifacial. So this is also technology coming up in a big way, and this gives more efficiency. Of course, this technology is costing more because of the double step. Basically, the top and the bottom both. Basically, the one unit is there, but the PN junction you have at the both side and the contact layers and the anti-reflection. Rest things are basically 2 times is there. The silicon wafer is there, but the front and the top, you are making junctions there. So it's a bifacial solar cell. So giving more efficiency compared to monofacial, but cost, it is going to cost more. Other is there. It's a basically this is called the interdigitated back contact solar cell (IBC). This is also now is quite coming as a common technology. Basically, you know that as in the beginning I have mentioned that the fingers you are making, the silver fingers, it is basically the trade-off. You need a contact so that you have a collection of the carriers, and also you need opening there so that your light can travel inside. So this innovation is taken place here. From the front side is a completely open. The light can go inside there. This is how completely no contact layer here. Huh? No metallic layer. Basically, all light can travel inside, and you can have a electron hole pair creation. But from the back side, we are conducting the carriers. So one side you have n-type diffusion, other side you have p-type diffusion, n-type, p-type. Negative contact, positive contact, negative positive. It's an alternate contact, negative positive, negative positive. So this way solar cell is designed. So this also gives you the good efficiency because you have a completely 100% open active area is 100% from the top side, so that you can have a maximum absorption of your sunlight. Now, the thin film solar cell, a little bit I will talk because I'm seeing and I want to try to manage my time also. As in the beginning, I'll give you 10 minutes for discussion. So in the thin film, this is also important technology. You know that the 3%, still now 3% market is there, and mainly it is basically for the CDT tech, CDT. A little bit I'll talk about the amorphous silicon because that's also important, because amorphous silicon technology is uh, coupled with silicon technology. We have another important technology that is called HIT solar cell, heterojunction intrinsic thin solar cell. So in the thin film solar cell, basically the thickness is less compared to your crystalline silicon. It's possible to make flexible, though crystalline silicon is also possible to make flexible, because if you don't use the glass, you can have some flexibility there also. So in the thin film, here it is given your motivation for thin film technology. I'm going fast. So like from the wafer, you have a glass like in the thin film, the first generation silicon, the thin film, and the foils is possible. Maybe, I don't know, solar paint people are talking about. You can have some paint and that can work as a solar cell. And the flexibility is also very important. So people, uh, this is there in the since long for flexible thin film solar cell, but somehow because of the poor efficiency compared to crystalline silicon, it is not coming in that way. But in the perovskite, people are working more on this, even in the roll to roll there. The technology is there, but because of the efficiency in the thin film, also again you have a choice of material. It's the same thing what I showed you, but the amorphous silicon up to 2010, this was quite popular technology in amorphous silicon. Those people who have worked earlier, 20 years ago, the calculator, the solar cell you might have seen, that is the amorphous silicon. The mature technology, but out of the market because the lower efficiency. Thin film crystalline silicon, a lot of work is going on, but not mature. Cadmium telluride is CD, it's toxic. Other things are there, but still, this is 3% of market is CDT. Copper is not coming in that way. Copper, indium, gallium arsenide. Gallium arsenide is basically for space application. Emerging PVs are there. So now, in the amorphous silicon, the compared to crystalline silicon, just I'll give you this. It's a non-crystalline material. You have a lot of defects are there, and these defects can be passivated using making it hydrogenated amorphous silicon. So basically, those silicon bond are dangling bond. If it gets a bonding with the hydrogen, your this defect, some defects can be passivated. So some opening can be available. Even in the tail state, basically these are due to the distortion in bond length and the bond angle because of its amorphosity. Some improvement can take place. So basically, this is how it looks like your absorption coefficient. The amorphous silicon considered to be a good photovoltaic material. But as I mentioned, it is now used in HIT solar cell, not as amorphous silicon. It's the gone technology now. But of course, this material is used in a lot of other application in the display technology as a TFT, thin film transistor. There is used. So this is made basically. You have a saline gas. You you are dissociating your gas in the PCVD chamber and you have a material. Now I'm going little fast basically, just I'm giving the glimpse of this because I'm not emphasizing. So you have a three chamber here, the silent N type you can make intrinsic layer because here you need PIN layer. So silane plus phosphine or the silane for intrinsic layer and silane plus diboron for boron. So it becomes a P-type material. If you want to open some band gap of that material, you can add carbon there also. This is being used as a methane. So basically silicon carbide gives you more band gap. This is the NPL facility for growing such materials. And you can have a single junction like amorphous silicon, microcrystalline silicon, or tandem junction, amorphous silicon germanium or amorphous microcrystalline. This amorphous or microcrystalline, all those. So basically, more light you can absorb. The single junction or the tandem junction solar cell is possible with amorphous silicon. And this, I think I have already explained about this. You have a monolithic integration. This is all for that. And this technology is there, but not in the market now. Means you can get some modules here and there, but difficult because most of the industries are closed or they have shifted to some other. Even in amorphous silicon, roll-to-roll process is there. This is a company, Unisolar in US. Basically, the company was owned by one Indian only, Sumendu Guha. And this was once upon a time, it was a good production of solar modules. Even on the stainless steel foils, it was possible to make the roll-to-roll modules. So it was technology was there, but because of the efficiency in the module, it basically is defeated against crystalline silicon technology when it comes. So now this amorphous silicon basically, if you club this silicon technology and the amorphous silicon technology, like if I take 18 to 20%, but now it is more, even 6 to 9%, you can get 25% efficiency of that. So this is how it looks like different. This is a conventional, as I already explained you. Here in the this HIT solar cell, this is called heterojunction with intrinsic thin layer. The intrinsic thin layer, basically it is a amorphous silicon. If you see that crystalline silicon, N-type FZ grown 100, this is the parameter for silicon wafer they have used. 300 micron here it is given, but not this technology is less than 200. Even some industries are working with 150, 180, 150 micron. You have an intrinsic amorphous silicon here. If you see from front side and the bottom side both, then P plus amorphous silicon. So basically your junction is forming here with your P-type and the N-type silicon. And this I layer is very, very thin, less than 5 nanometer or sometimes maximum 5 nanometer it is used. This is for passivation of crystalline silicon. So this passivation basically improve the overall efficiency of this cell, and over you have a homojunction. This is a heterojunction amorphous silicon. And also in the bottom side it is done, then ITO and AG. ITO is for collection, transparent, light can go in, and you have a metal contact. All thicknesses are given here. So basically how this looks different from the conventional crystalline silicon, amorphous silicon based heterojunction solar cell. This is also quite popular nowadays. And this is much, much better. Just in the previous talk, I entered 10 minutes before. I was listening that the one question was asked for the temperature. Of course, under the temperature, performance of solar cell deteriorate. But this is what the beauty of amorphous silicon. That is basically one has to measure the coefficient parameter, temperature coefficient parameter. For crystalline silicon, it is much, much higher, like 0.5 degree Celsius percent per degree Celsius. Here it is only 0.2. So degradation is less. Basically, like Rajasthan like places, this will work much better compared to crystalline silicon. And the power loss 1% for every 2 degrees Celsius increase. This is, and the other advantage of this, because these conventional crystalline silicons are made at 900 degree, because the you have to go for the diffusion of your material to making a junction, PN junction, and that temperature you need at least 900 degrees Celsius. But here you can grow less than 200 degrees C. You need a PCVD process like I have shown you. Amorphous silicon, one can grow good quality amorphous silicon at 180 degrees C, even intensity and the doped layer. So this is what says advantage here. The one is you have a lower temperature coefficient and the lower temperature for making of the cell. So it's the added advantage here. The advantage of heat solar cell, of course, some cost one say because of the multi layers you have, but still now lot of competition is going on in the market with the perk solar cell and the heat solar cell, even with the TOPCon and the heat solar cell. They are competitor to each other, these two technologies. This is just I want to emphasize. Other thin film technology is CIGS technology. Here you have a absorber layer is a CIGS, and you have a then buffer layer, and then you have a CDS. This you can grow as, or sputtering you can do. Sputtering is a process that I'm not going to tell because it will take much time. Even thermal evaporation one can do, like here figure is given for thermal evaporation. You have absorber layer, and this is grown on the substrate that is on the basically soda lime glass. It is being used. Over that you have to place a molybdenum layer. This is back contact, and then absorber layer, your buffer, this is CDS, and then you can place ZNO, and this way your device is fabricated. This is CIGS. Of course, it is a commercial module. Basically, it is commercialized. You can get module in the market, but it's not that popular because of the efficiency compared to CDT. CDT is quite popular. And in the CIGS also, it is the monolithic integration takes place. Like from the soda lime glass, back contact, isolation, the first P1, basically you have to cut the with the laser, you have to scribe, make the lines, then you can go for the absorber and place the CDS, you have a PN junction over here. Then again you do the mechanical patterning here, and then you have a window layer isolation, then P3, that is the laser scribe. So this way you have a monolithic integration, and then we go for the lamination like EVA or the glass, like I've shown you in the crystalline silicon. So that is common here. And secondly, if I go for the CDT here, like the CIGS, you have a CDT and the CDS. Here also the CDS. HRT basically is some TCO with high resistance value, then the TCO, and over the substrate it is grown, and the top electrodes are formed. So this is 3% right now. 3% market is of the CDT is there, CD thin film cultural, right? But of course, problem is the toxic of this material, cadmium and the tellurium there. But this is there in the market. In the multi-junction solar cell, in the beginning, I have also mentioned that you can have a gallium arsenide based solar cell efficiency more than 45%. You can achieve. Basically, these are the concentrated, more than one sun. This is for, I think, more than 500 sun it is given. For the single cell, single sun, you have a 36% efficiency is possible. Here, indium gallium phosphide, gallium arsenide, germanium on germanium substrate. It is there. Like if you see here, this is for your gallium arsenide. So this is not for our terrestrial application. Basically, it is only for the space application because this material is very costly. The silicon you can get 10 rupees, 12 rupees per watt, but this is very costly. And if you see, this is how it is shown here, your internal quantum efficiency with the wavelength of each cell. Like you have here three cells, the top cell, middle cell, and the bottom cell. Bottom cell with band gap this, germanium and gallium arsenide 1.42, and gallium indium phosphide around 2 electron volt. So this is basically, if you see the blue spectra, this, and this is basically the current it is being produced in the top cell. So light from 300 to 700 it is shown, it's how it is absorbed, and the current is producing 16.3 milliampere per centimeter square. In the second cell, you have this much spectra absorption. Current is also quite close to this, 17.5. And in the bottom cell, it's a germanium basically. If you see here, So 24.724. So this is how. But you know that in the simple electronics, say in the diode, if you are connecting in series, so whichever the lowest current is producing, that will add to it. It means even if this cell is producing higher, it is not going to add. The 16.3 plus multiply by 3, that what you are going to ultimately your current here. So in the design, this is very, very important that you need to proper couple basically the one cell and the other cell. Some interlayer you may need properly so that whatever the current is produced, that transfer to that. And also it is always good to design cell so that equal amount of current produced in all the layers. In the design, you can choose the thickness of the layer, different thicknesses also you can choose depending upon what the solar spectrum it is going to absorb. So it means first you well characterize your layers. The layer structure, that is the most important. Then you do the optical measurement of that, spectral response of that layer, which wavelength is getting absorbed and how much current it is producing, and also the electronic properties there. You measure the carrier concentration, the nature of carrier, whether p type or n type, semiconducting property, and then their concentration, carrier concentration. And if defect, definitely material will possess some defects, so also it is important to see the defects in these materials. The well characterization of materials first, then if you are forming the junction, the individual cells characterization is needed, and then you go for the integration of these cells with proper interlayers. That's what it is, the requirement for making any multi-junction solar cell. Okay. So this is a figure given for the concentrated solar cell. So you have cell like here, the cell is there. Here, my arrow, what I am showing here, cell is here, and your light is coming on this dish, and that is focused at the cell. So more than one sun is there. So this is how the concentrated solar cell is made. Now, organic solar cell, basically, I think in the beginning I have shown you the donor and acceptor here. Even in the perovskite solar cell, hole extraction, electron extraction, with the ETL and STL. And these are the different combinations. Lot of research is going on. In my laboratory also, we are quite working on this material, even with vacuum and non-vacuum. Different processes are there. Spin coating is the most common technique. Then you have a slot die coating, printing coating, doctor's plate coating. Even in the vacuum operation, sputtering, PCVD, we are also doing that, all the techniques in my lab, but still we are struggling with the stability issue. Like this is one work of NPL. Basically, this is the NPL slide I'm presenting here. This is the printing printer we have developed at NPL, and we have made cell on 30 centimeter by 30 centimeter. The first we characterize the material, structural properties and optical properties, and then we go for the solar cell. This is for SNOT, ETL we have used, perovskite, and the P3ST, STL, and we made the solar cell. So this is for one of the device area, 9.45 millimeter square of this efficiency of a module. Basically, this is for module, and this is for some cells, some more improvement here, 16%, 19, 29, 19% some. And also basically, as I mentioned, the stability. So our more focus is now towards the stability study so that we can arrest instability in this material. Unless this is done, nobody is going to commercialize this. No industry is coming up for. Though industrial research is also going on this, even this flexible, some other modification we have done, we have made. This is also NPL work. I'm going fast here. These are some facility required, and we have some facility in NPL for fabrication of materials, and the solar cell, diffusion furnace, multi-chamber PCVD, some IBCV tester, rapid thermal. This is for lifetime measurement, 4 probe, and this is a laser scriber. So basically, these facilities are in the clean room, the cell fabrication and this characterization. So basically, when you want to make a good quality material, you need some these facilities, and you need characterization for this. This is for our perovskite. glow boxes are there. And this is again, if this we can do up to 6 inch by 6 inch for solar cell, silicon solar cell, for organic and perovskite solar cell, 4 inch by 4 inch. This is for fabrication. Okay, so now I'll some briefly, I will touch 5 minutes or so for flexible. You know that flexibility I have shown you. Here, basically in the silicon flexibility, now I talked about perovskite, organic, all those flexible thin film is there. But even the silicon flexibility, that certain amount of flexibility is possible if lower the thickness up to 50 micron or so. This is what, so normally 180 micron is the conventional thickness. Some industry have trying now 150 micron, but this is now 180, 200, 180 to 200 technology is there nowadays. So if you make your silicon 20 to 50 micron, your silicon will become flexible. So this is what, this is the NPL we are working. This is all futuristic technology. It is not that it is commercialized or modules are available. We are doing R&D so that in future some technology can come. So this is basically the very flexible. It's a silicon. Just again, I'm mentioning is a silicon. The 50 micron silicon. You see, this is bended, and over that we perform the texturing. Okay, and then we made the solar cell on that. So this is again some work. This is different work. So basically, different materials we have used, and solar cells are made on flexible. These are heterojunction solar cell involving inorganic. Your inorganic is silicon, some organic material like here P.PSS is used. And now the silicon heterojunction cells with flexibility. Some this is other results. If you see, like here it is given a comparison 56 micron, 57 micron they have made, and this is a normal 280 micron. Sorry, yeah. So if you see, they have produced some good efficiency here and perform the micro texturing. This is a spectral response, basically in internal quantum external quantum efficiency of three kind of cells of different thicknesses silicon. So this is a newer area, emerging area now, because two advantages will be there. One, lesser amount of silicon will be used. Lesser means your cost will be low, and secondly, you can have some flexibility there. The flex, if cells have flexibility, it finds some its applications there. So this is also one emerging area. Make silicon thinner silicon to save the cost and to make flexible. This is for perovskite and silicon tandem with flexibility. These cells are made with 83 micron, and perovskite is here, and this is what they are external quantum efficiency they have shown for top cells and the bottom cells, and the efficiency parameter. This is all recent work basically. So this is also one emerging area. Another perovskite silicon heterojunction tandem solar cell, the Longi, basically is a Chinese company. They are doing good R&D. They have produced that. This is a record efficiency, 34.85% of a tandem junction solar cell. Basically, there's the crystalline silicon and the perovskite solar cell. So they have connected these two, and it's all recent. If you see, this is for 1 centimeter only, a small cell, and these are the parameter BOC and ISC with fill factor, good fill factor, 83%, more than 83%. This is a company, their R&D. So this is how basically the silicon heterojunction, that's it's again the heterojunction, you see, amorphous silicon. So this is mostly people are performing the crystalline silicon with amorphous silicon and then perovskite. So these three things are there. In recent time, the thrust area to make silicon perovskite solar cell and the silicon solar cell with the heterojunction involving amorphous silicon. You can have a 2-terminal device, you can have a 3-terminal device, you can have a 4-terminal device, but this is preferred one because this gives more efficiency, losses are less, and it's not that good. So here, if you see with time, it is shown for 2-terminal devices. So this is what the 34.85 I was showing for Longi Solar, the maximum efficiency they have produced. Even with the area, basically this is what I was telling to you. In the perovskite, you are getting good efficiency, but the scale and the stability is a major issue. So that is important. So people are working to making larger and larger devices. And if you see, people have worked some, they have demonstrated good efficiency with the larger size, but somehow they are facing, this is very crowded. But just I emphasize you that their devices not run for larger time, they degrade with time. So this is a major issue. Maybe you can read this paper came in Nature Photonics recently in September 2000. You can note down this reference. So they have shown means the different groups they are addressing the lifetime of these cells, and it's very important. Unless we solve the this issue of stability, basically why this stability? Because you know that perovskite structure is ABX3. Your A there BeX3 elements are there, like in the methyl ammonium lead iodide. So lead is there and is a heavier element, and because of the ion migration, the structure gets collapsed because of the external stress, or even in the internally it is formed once it is in the operation or in the field. So that's basically the major concern in this material, and proper passivation is needed. So that's all work is going on so that we can make the stable perovskite. Once perovskite is stable, then only it will work with the silicon technology. So this is how the markets share. If you see, with time things have changed. In the beginning, I was showing you from the BSF. This line is for the BSF. Okay, the BSF has gradually down, and in 2023-24, no BSF. Now you have a PERC. This is your PERC technology. So from BSF, PERC has emerged. Okay, the crystalline silicon, the silicon heterojunction is also coming up. And if you see, this is how the with time very fast technology is changing. So one has to evolve very fast. Even this Topcon is there. So things are changing very fast. So that is why. So maybe it is now 9:20, 2 3 minutes I will take, then I will complete it. Because I feel as for the solar cell design and the things I have covered, but the most important, because you need the technology is changing very fast, and the solar module has its life, 25 years. What this manufacturer gives you a warranty of this, yes. And why 25 years? Basically, the modules degrade at a rate of 1%. Generally, it degrade at a 1%. It means 80%. When it gives you power of 80% after the 25 years, then it goes into the end of life. But there is no standard for it. This is just widely accepted rules. It can go below that also. So with time, this is how it is given. And sometimes it go earlier also, the models. So it means lot of solar waste is going to have how it looks like. You can have a early end of life or its normal life. Normal life is 25 years or 30 years, but early life means 15 years, 10 years. In the both cases, we have a lot of solar waste. It means solar waste is there, and this is how it is projected. The global solar waste of 212 metric ton by 2050. India has also projected this. I was also the part of this in this estimation with one of the our agency that is called CEEW, that is Council of Energy, Environment and Water. So we have estimated that by 2030, about zero point 0.6 metric ton of waste will be there in India, and 19 metric ton by 2050. So 1 megawatt produce about 95 tons of module waste. This is a convention. And NPL nowadays is working a lot towards development of a solar waste, basically recycling, so that we can extract material. The NPL have extracted all the material from solar waste, and also we made silicon ingot of 99.945 purity. This all is available is on different uh, channels basically, and we have recovered about 92.4% of efficiency. Actually, I'm giving you just only the NPL data, and of course NPL was the first started this work in India, and we were the globally first. We made the silicon ingot using recycled silicon. You can find in the literature also, and this is how the ingot we have made. And density is ideal, means the theoretical density of silicon 2.33 we made with the 4N purity. This is what, and this is basically okay. And now for the thin film solar cell also we are doing recycling for CDT, amorphous silicon, and the perovskite also. In my lab, I tell to all students, even my colleagues also, don't throw this perovskite solar cell in the dustbin because the lead is there. You know, the methyl ammonium lead iodide, mostly that material is used. So lead is there. It is going to harm our environment. If you throw it, go in leaching as a leaching to the water body or the soil. So it's not good to throw. So basically, we collect it, we recycle it, and the extracted tissue coated glass we use for making of again cells. So this is what we are emphasizing in NPL. And there are technical challenges basically for circular economy approach. The cost effective, efficient eco recycling material recovery process is needed. Purification for silicon, fast changing silicon technology. As I mentioned you, lot of silicon technology is there, complexity is there, variety of design is there. So that is why easy recyclability is needed. The design of PV module system for easier recycling. It's a very important area. We are working it, though I am not presenting here. What more we can do here. So with this, and since the time given to me to leave 10 minutes ago, so still 7 minutes is there. So basically the silicon technology is there, BSF, PERC, all those things are there, and this is a dominant technology, and it will be there. Emerging PVs are there, perovskite silicon, but unless the uh, perovskite stability issue is not solved, this technology is not going to come. And the recycling, again, it is important because the extraction of material is a very important, very important. You know, the cost of silver is going up, and this is for maximum silver is being used in solar industry, and other industries also using, but maximum solar. So that is also the one of reason now in the you can see the market, the solar and this silver cost is going up. So basically the recovery is very important, and newer design is needed so that easily recycle can be done. So with this, I thanks and I sincerely acknowledge my colleagues and the students in NTL. So
Thank you, sir. Any questions from audience side? If you are having any question, just unmute yourself and ask the question. So there is one question that during the fabrication, is it placed layer by layer or only one layer is surrounded by another layer?
no, it's layer by layer. In the solar cell, is layer by layer. At least you need PN junction, or if it is embedded in the material P type and N type in a layer, so then also you need contacts from the both sides. So 3 layer is the minimum there. This is a layer by layer.
Okay. Thank you. Anyone having any question?
Hello, sir.
Yes,
It
please.
was really a nice talk. Sir, in thin film, you said it is with vacuum as well as without vacuum. So,
Yes.
is there any difference between these two?
Yes, difference is there. In vacuum, basically, you know that the vacuum, basically you can avoid contamination of the background gases. When you are doing any material processing in vacuum, and if you are doing in non-vacuum environment, it means there is a chance of contamination of residual things there available in the atmosphere. So vacuum process is a cleaner process compared to non-vacuum process, but the vacuum process involves lot of cost because you need vacuum system, all those infrastructure. The cost is definitely added to it.
Thank you, sir. Sir, second question is multi-junction cells photovoltaic systems are commercialized?
Yes, it is commercialized. As I mentioned, for amorphous silicon, it was commercialized. Cells were available, but since at that time efficiency was only 10%, on the other hand, crystalline silicon was also 14 to 13 to 14%. It was not surged in the market because in the 2007 to 8, that was the transition period. Because a lot of R&Ds were taken place, was going on, and also the scale up of the production was there because of the Chinese big aggressive production that makes the cost lower for crystalline silicon. So as for your question, multi-junction solar cells were commercialized of amorphous silicon, that was there. Right now, that is not available. And secondly, it is available for space application, that gallium arsenide based. So one can get those cells, great difficulty for own use for small size cells, but for space it is available.
Okay. Thank you so much.
Any question from audience side? Okay. I think there is no question from audience side.
Yes.
Madam, just check chat box.
So there is no question in the chat box. The question which I have asked, that was available in the chat box only.
There is one question, I think. What is a chalcogenide perovskite and how is it different from oxide and halide perovskites? Asked by Surya Chandri.
Yeah, this question is there. Yeah, one question is there from Shurya Karthik Chellori. Yeah, your question is about the metal halide. Basically, halide perovskite is ABX3, as I mentioned. It's depending upon the element you are going to use. But in the this solar cell, this is basically the metal halide perovskite is used. Now, as for your general question, the chalcogenide perovskite and how it is different from oxide and the halide perovskite. So chalcogenides materials are there, and in the oxide, oxygen-based oxides are there, and the halide, it is basically the chlorine, bromine, or iodine is there with along with the metal. This elements difference, but in the solar cell, it is mainly the metal halide. Halide perovskites are used.
Okay, thank you. Sir, it's a request from audience side that you can share the PPT with the Gate, sir. Whenever
Sure.
whenever you will permit the time.
Yeah. Okay.
Yeah,
I'll share.
yeah. Thank you. So I think
Okay.
there is a question from the audience side. So, respected dignitaries, esteemed speaker, Dr. Sushil Kumar, sir, faculty members, coordinator, and dear participants, on the behalf of the Department of Electronics and Telecommunication Engineering, AC Patil College of Engineering, Navi Mumbai, I sincerely thanks Dr. Sushil Kumar, sir, the Chief Scientist, CSIR NPL New Delhi, for his insightful lecture on solar cell design and fabrication. His valuable inputs on advanced solar cell design and fabrication have greatly enhanced our understanding of the subject. The discussion on losses during fabrication highlighted important research gaps and open avenues for improving efficiency and reliability in solar cell development. I also extend my gratitude to the Atal FDP Organizing Committee, our respected management, faculty coordinators, and all participants for their support and active participation, which made this session successful. Once again, thank you all for your valuable presence and cooperation, and special thanks to our today's guest, Dr. Sushil Kumar, sir. I request all participants to submit the feedback for both sessions separately till late night today itself. So, with the permission of the FDP coordinator and committee members, I declare that today's session has been successfully concluded. Thank you, one and all. Thank you, sir.
Okay. Thank you. Namaskar to everyone. Thank you very much.
Thank you.
Ma'am,
Good
Thank,
night,
thank
sir.
you so much.
Thank you, sir. Thank you, sir.
share the
Thank
feedback
you.
Thank
link.
you, sir.
Okay. Bye bye.
Yeah, bye. Thank you.
Thank you, sir.
Thank you, madam. Thank you, Anada, madam.
Welcome, sir.
Thank you, sir.